AI. And Lincoln will explore groundbreaking advancements in combining SQL and Flink for modern data and AI applications. So let's welcome.
Sorry, is there a typo with this title? Start STUFF. Shouldn't be SEAFF.
Okay.
Okay, but let's fix it later. And let's welcome Lincoln to the stage.
Thank you. 对，麦不用了吧？这儿有一个麦，需要是吧
Yeah. Good afternoon, everyone. Yeah, I'm Lincoln, the staff engineer from Alibaba Cloud, and I'm also the PMC member of Apache Flink. Today I will share you a topic about the circular advances for data and AI in the coming Flink 2.1 release. Next slide. Yeah. Then let me outline the structure of today's talk first. We will explore three parts. For first, data and AI. Here I will introduce how Flink enhanced the support for AI functions, bring users to bridge the real-time processing with AI capabilities. And also for the optimized joins, I will introduce you two important optimizations, including the data join and the multiple way join. And lastly, I will share some roadmap for the future improvement. Okay, next slide. Yeah. Before we dive into Flink's new AI functions, let's start from a real-world case. Next page. Yeah, maybe some of you already see the similar case for today's keynote. This is a real-world case that do the product compliance check. Imagine you are running a global e-commerce platform, and we have got sellers uploading millions of product listings every day. Here's the catch. In different countries, it has different local laws. We have to make sure that every single listing applies the local rule. And for the team, they try to use Flink to build a pipeline to help human review. As the picture shows, we firstly read the product listing events from Kafka, and then implement a customer UDF, says keyword matching UDF, to do keyword match, rule-based keyword match, to detect if the product title violates policies. And lastly, output those risky titles of product listing to the output topic for human review. But the problem is the rule-based systems always super rigid. Let's see the next slide. Here, let's see the two concrete failure case for the rule-based keyword matching. The first case is overblocking. Let's see the title, a product titled grape juice, no alcohol. Then the keyword contains the keyword alcohol. Then it triggers the rule. But the product title explicitly said no alcohol. But the rule cannot distinguish it. So it is a false positive, and wasting the human reviewing time, and also risking customer frustration. And the second case, underblocking case, when the product title named natural vanilla extract, yeah, it has no keyword alcohol or wine, so the rule-based system cannot find the product. But actually, we know natural vanilla extractor often contains alcohol because it's methodology. And this false negative always usually cause critical punishment. So for this problem, how to leverage AI's semantic-based analysis to address this problem? Let's see the next picture. Yeah, let's test it with AI to see if the AI works better. This is a simple example with ChatGPT. But remember, this can be any LLM or customer model you train. The first step, we give the model a prompt, clearly told it its role, the rules, the examples, and the task. Secondly, we feed it with the problem case we previously hit. And we found the AI model works better. It can clearly, correctly recognize the problem. So how do we integrate the AI capability into our pipeline? Yeah, let's try to see what happened next slide. Yeah, we have tried to integrate AI to the UDF. We redeveloped LLM UDF. The UDF just directly connects to the AI model, and when, yeah, the overall data flow stays almost the same as before. The only difference is we upgrading the UDF. When a product title event arrives, the UDF just send the title to large language model, and it returns the decisions, and we output this risky output to the original topic for human review. So this looks perfect, but it doesn't work fine for more large scale. Yeah, next slide. Yeah, at first it works great, but the hidden cost is when we want to switch the models, for example, switch from OpenAI to Alibaba Cloud, we need to rewrite the code. And if we want to test different models, then code need change again. Yeah, this approach doesn't scale. So every time the model or API changes, we all need to change the code. And for the execution, we use a synchronized execution first, but synchronized request commonly means traffic jam. Take an example, when a product title requested to the large language model from 1 to 3 seconds latency, it will perform low throughput. And if we want to use the async request to gain higher throughput, then we need to rewrite the code again to use Flink's async Scala function. Now we need to pay more attention about the async callbacks and also the error handling. This is not fun, and there must be some better solutions. So let's see how Flink 2.1 supports the circle native AI function to address these problems. Here is how the functions work. First, use a create model syntax to register a model, either kinds of large language models from different providers. So you can see a single SQL command can do this. The model management can be easy. And for the AI functions, we support model predict for both chat completion or inference task, and also the embedding task. Yeah, for chat and for chat and completion, we can generate results from the text, and for embedding, we can help to build vector embeddings from text and then put them to other systems like Elasticsearch or Milvus. Next. Yeah, let's put it together to a concrete example, the previous product compliance case. Now, we have re-implement all pipelines using SQL. First, we just create a compliance model using create model syntax and use the model scope provided from Alibaba Cloud. And when we choose a text model named Qianwen2 and give a system prompt, tell the AI its role is a product listing review expert. Then, if the product title, the tricky case arrives again, the AI Flink send it asynchronously, use an asynchronous request to the model. And the model returns the response in a JSON format. Then we finally output those risky titles to the output topic. In this way, we can simply use SQL to achieve the goal to upgrade the former rule-based analytics to the semantic-based analytics. In the next slide, let's talk about two practical recommendation for async configuration and resource planning when running AI functions. Async execution can be the first choice because we can use Flink's async execution the more cost-effective way compared to set task parallelism, because it's more lightweight. And you can see just set a single option can enable the async execution. And we recommend users to set allow unordered output mode if the input string is append only. Then Flink may process data faster. And for the throughput, we can set max concurrent operations matching your LLM's capacity. It can be friendly to matching your target throughput. And another thing you may care about is the timeout. If you don't want to long tail request trigger the task failure, you can set a timeout larger than the AI's max latency. And the second part is resource planning with the Little's law. We can apply this formula when do resource planning. Here, L means queue length. It's related to max concurrent operations. Lambda means arrive rate. It's related to target throughput. and W, the average wait time. It's related to average AI response time. So, for example, if we want 100 QPS target throughput, and let's say the 99th percentile latency of AI is 1.2 seconds, then we need 120 Q lengths. Also, we need to pay attention to the memory setting in Task Manager. We should kill the Q length and the average row size of the data. Yeah, next slide. Yeah, before we dive into the join optimizations, let's talk about something foundational, JSON. Next. Yeah, let's start from a simple fact. JSON is everywhere. Yeah. We see JSON in event logs, search document, AI payloads, from traditional data pipelines to the new AI workflows. JSON is very important format to express representing the semi-structured data. And for RAG pipelines, the RAG system also relies the JSON to store and querying documents. Even the LLM, the prompt and the output commonly use the JSON format. So far, Flink SQL support a lot of built-in JSON functions. Next slide. Yeah. From surface, we can see like JSON value and the other similar functions can make it easy to access data inside a JSON string. Yeah, as shown in the picture, the example JSON document is a nested structure. When we need to access the $.metadata.device field, we need 5 steps to pass all the JSON to get the field value. Because JSON is not schema awareness, and there's no indexing inside the string. So the circle planner cannot do optimize for the accessing. Next slide. So in Flink 2.1, we introduced a new variant type, a circle native binary encoded effective semi-structured type. Unlike the plain JSON string, it stores both metadata and the value in a structured way. For the similar access scenario, when selected data.metadata.device, it is a fast lookup by the offset. Compared to the previous one, it's just 2 steps to do this. And sorry, the previous slide. Yeah, Flink 2.1 support give basic support for variant type, and there will be more optimization, as just mentioned, for the optimizer, something like project pushdown, filter pushdown. This threading for optimization for reading will coming in future releases. Next. Now let's move to another core challenge in streaming data processing, the joins. Flink SQL support a lot of kind of join types: regular join, interval join, temper join, lookup join, and more. Each join is designed for specific case. Among them, regular join is most intuitive. It looks exactly like the traditional circle join. So this makes it very easy to write and understand. So when users use a regular join and use it properly, let's say commonly on a small to medium-sized data set, it performs very well, both high throughput and low latency. But it is a classic trade-off. Simplicity and flexibility often comes at the cost of scalability. When the input string grows bigger, because regular join relies strongly in Flink's data backend, buffers all the input data in its state. And the regular join has two state storage, the left state and the right state grouped by the join ID. For example, we have two Kafka strings, the page views and the orders. They were joined on the common product ID column. When event arrives, the regular join operator will perform a lookup to seek the matching entries in opposite state table. So it relies the full state of input. When the input grows and the state becomes more and more large, the job will be unstable. You may see long time checkpoints, slow access to state, and you will also see the latency spikes and back pressures, even the checkpoint failure. So how do we fix this? Let's see the next slide. Yeah, that's where the data join comes in. It can decouple the internal state to external systems like Flux. Many of you may heard this project. Flux can send changelog updates continuously and also support fast index lookup. So when a new event comes, the dirt join will perform index lookup directly in Flux, just like a key value store. So no local state exists, and all larger state issues disappear. Yeah, next slide. Here's a summary that what we have observed in production. For regular join, we see a pipeline that grows a big state, more than 100 terabytes state size, and the checkpoint duration increased to 90 seconds. And it will lead unstable maintenance. The long duration checkpoint also complex recovery. So after upgrade to data join, it is stateless now. It eliminates all the big state, and the checkpoint duration reduced from 90 seconds to just 1 second. And it cut CPU and memory resources more than 80%. And because it's stateless now, we needed to bootstrap the job with state, and we can use a batch style job to do the bootstrap. So it can finish the work from 4 hours to just 30 minutes. And another game benefit is the join operator now is traceable. Before this, the regular join has a black box state. Yeah, circle stateful operators always hard to trace because its internal state table is a black box structure. It's hard for users to do data inside. Next. Yeah, for the regular join, let's take a closer look at another hidden cost, especially when we do multiple string joins. Regular join is binary only. It can just join two strings at a time. So if you want to join multiple strings, for example, 3 strings, T1, T2, and T3, Flink will build a cascaded join plan. First, T1 join T2, and then the result join T3. Every join stage will keep its own full state. So you can see the T1 join T2, the intermediate result will, this data will get stored again in the second join. It's a bit redundant. And if we have more strings need to join, the amplification will be more larger. Yeah, next slide. Multi-way join is targeted to solve this redundancy because it supports to join multiple strings on same join key and in just a single operator. So as illustrated in the picture, there will be no intermediate state again. So this solution will efficiently address the redundance problem and has no longer the cascaded checkpoint delay and spikes. And if you have the more strings you have, the more benefit comes from this solution. Next page. Yeah, then let's talk about the roadmap. What's the next picture? Yeah, one near-term goal is to enhance the support for the end-to-end RAG pipelines directly in Circle. Yeah, for former introductions, we see the example of model predict that can do both embedding and inference tasks. And also, users can extract vector embeddings from text and put them into systems like mirrors. But retrieval is not supported yet. And the vector search function support will add this piece. After integrate this, users can do end-to-end RAG fully in Circle. It can be a fully directive RAG pipelines. This will simplify the RAG pipeline a lot. Next. Yeah, we are also expanding the scope for integration with AI functions. So there will be more scenarios to support. We are support for the multimodal, not just the text, including the audio, video, and images. And another thing is model evaluation. This function can help users to check the model's output quality just inside the same pipeline. And after all these functions integrated, we can support more scenarios. Next picture. Yeah, join optimization still remains a focus. And as data join has decoupled the state storage into the external system like Flux, we are also plan to supporting systems like Apache Pymon to help users to achieve near real-time data join. And also, we will support more query patterns, relax the schema alignment, and also multiple string joins. Next. Yeah, to recap, this is the key takeaway of today's talk. Flink SQL for data and AI, we have introduced the SQL native model management and the integration with AI functions so that users can use SQL to do all the work. And the effective variant type support give us a chance that we can do performant processing with JSON at scale. And another thing is addressing the streaming join challenge. The two important optimizations, both data join and multi-way join. And for the roadmap, we will support more functions, scenarios for AI pipelines, and also for the join operations. Yeah, this is all the content from my talk. Thank you.